During the previous section of work, we were looking at the higher power connectivity matrices. What that was telling us was where there were 2 steps between nodes or where there were 3 steps between nodes. Sometimes you might want to look at more information regarding this. And we might look at where we've got at most 2 steps between nodes. So that would give us the results where we've got 1 step between nodes as well as 2 step between nodes. So this is the matrix C plus C squared. We can also look at the matrix C plus C squared plus C cubed, which gives us the number of roots of at most 3 steps between nodes. This can be particularly useful when looking at networks of trains, or we might be looking at networks between connectivity as well. So if we look at this example of a train line between here, you can see we can get from A to B, and then also B can go back to A. Alright, so we have this connectivity matrix here of C, and just by confirming, we can look at from B to B, there's 3 possible ways. So we can go B to A and back to B, B to C and back to B, and B to E and back to E. So we get this value of C squared. We also get C cubed here, where we're looking at 3 steps between. So you can see there's a high connectivity between B and C by this number of 6. If we take it 1 step further and add this information, so we're looking at the solution that gives the number of roots of at most 3 steps between the nodes. Alright, we can see that each node is connected, so it doesn't matter where we go, we can travel between any 2 nodes on the network. Whilst we might need to not travel between A and A, we might need to return to A. So when we're considering a train line, we need to be able to get back to our starting point as well. Alright, and this can occur between any of those nodes. You can see that that connection between B and C, which happens to be 8, is actually quite high. And sometimes we might look at that information and see whether or not we want to reduce that. So we're just going to spend some time having a look at an example. So we've got to have a look at the network here alongside. So the first thing we're going to do is find the connectivity matrix. So we're looking from P, Q, R, S, T. When you're doing solutions to this work, if you can try and keep it in alphabetical order, that's what the answers in the back of the book will do as well. So our connectivity matrix, if we're looking from P to Q, there's no direction matrix there, so that'll be a 0. We can see there's no loops in our work, so that diagonal is also 0. Alright, if we go from P to R, there's no connection there either. P to S, there's still 0. And then we can see a connection from P to T, so that's our 1. So Q to P, we can see a connection there between the directed network. Q to R is 0. Q to S, 1, and T. So if we just complete this matrix, 0, 1. Alright, so now we've got our connectivity matrix for part A. Alright, so now what we want to do is find our value c plus c squared. So what we do is, using our graphics calculator, we're still going to put our matrix in on our graphics calculator, which is going to consist of a 5 by 5 matrix. And when we return from that on our calculator in the run menu, okay, we're going to use shift 2 to get our matrix. So matrix, if you're using matrix A, so alpha A plus, and then we'll use our shift 2 again to get matrix, our alpha A, and then we're just going to use the x squared button. Alright, so you'll be able to see on your calculator, it'll actually look like mat A plus mat A to the power of 2. And that'll give us the solution to c plus c squared. So c plus c squared, hopefully we'll get the same. So we should get 1, 1, 0, 1, 1, 1. So what we can see is there's still some connections that we can't make at the moment. So the values where we're getting 0, that means those nodes are not connecting to each other at most 2 times. Okay, so when we're looking at treble, alright, so when it asks what do the zeros mean, so we can see we've got zeros here, 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 and here. Alright, so what that means at the moment is it is not possible to treble. Oops. To treble between the nodes in 2 steps or less. So in our case, it's not possible to travel from P to R. So if we look at where P is and then to R in 2 steps or less, so by going over just 2 edges. So we can get from P to R in 3 edges, but not in 2 edges. So if you wanted to, you could continue to write, so therefore it's not possible to travel from P to R, R to R, R to T, or S to T in either 1 or 2 steps. Which you could finish off. So not possible to travel from P to R, R to R, R to T, or S to T in either 1 or 2 steps. Alright, this final matrix, there's no high efficiencies. It is important to consider the interpretation at the end. So sometimes if we had zeros in our production line, it might indicate that there's some inefficiencies or problems in the system. If we've got 2s or 3s with higher values, it might include an oversupply. So we might look for redundancies or reductions. So if you consider a road network, which is very similar to the train network before, a high level of connectivity may be considered to be wasteful. Whereas in an electrical grid or maybe a computer network, if you've got a high connectivity, then it actually might be a safety measure that's been put in place. Alright, so it's really important that when you're having a go at these questions that you consider what are the final numbers giving you, because that'll be important when you come to your test.